Okay, good morning. This is Professor David J. De Los Reyes. The date for this morning is actually March 23, 2023. The time is 2:20 a.m. Okay, good morning. My topic for tonight will still be advanced mathematics, and the topic is advanced mathematics lesson number 23. And I will now be presenting the solution of a series, a resistance in a conductance energized by a direct current source. We are to solve for the current using Laplace transform. This is lesson number 23. The given circuit, actually we have solved this one already by using the classical solution, the so-called differential equation solution. Again, we will try to solve the same problem, but the solution will be by using Laplace transform, meaning we are to solve for current as a function of time. And from the previous classical solution, the current is actually, as we have produced the solution, the current as a function of time is actually E over R e raised to minus T over RC. So meaning to say, again, we have to bring out this equation here by using Laplace transform. Okay, let's proceed. We are given a direct current circuit, a resistance in a, what you call this, capacitance. They are connected in series, so this is series. Energized by a direct current source. This is plus, is minus, this is the voltage source. This is the switch. So upon closing the switch, there will be a circulating current, and the problem is asking what will be current as a function of time using Laplace transform. Okay, let's proceed with the solution. As always, we will take the summation of the voltages around the closed loop upon closing the switch, meaning the summation of voltages should be equal to 0. So plus A minus B sub R minus B sub C, and they should be equal to 0. Okay? Substituting values, plus E should be equal to, I will transpose both the negative terms on the right. So what comes out will be B sub R is the product of current times R, and B sub C is actually 1 over C times the integral of I dt, where the integral of I dt is actually, this is Q, the charge on the capacitor. But in terms of current, it should be the integral of I dt. The charge on the capacitor is actually the integral of I dt. Because I think charge Q is actually di over dt. And to solve for di, it should be Q dt. Then, what do you call this? Q, it should be something like this. Current is actually dq over dt. Right? So dq now, I will put capital Q equal to I dt. This Q here refers to the charge on the capacitor. So if we try to take the integral of both sides, the integral of dq will be simply Q, and this should be equal to the integral of I dt. So this value, the integral of I dt, is actually the charge on the capacitor. Okay? Let's continue. Take the Laplace transform of both sides. E is a constant. The Laplace transform is actually E over S. And the Laplace transform of Ri, it should be R times the Laplace transform of I. But the Laplace transform of I is actually capital letter I as a function of S. Plus 1 over C. I'm following this. The Laplace transform Laplace transform of the integral of I dt, I have given you the so-called derivation of that, and as an equivalent, it will be, I will just follow this 1 over c over here. 1 over c, okay, it's actually 1 over s, I as a function of s, plus 1 over s, this is s, okay, I sub 0 plus, close bracket. That's why the last time around, I derived the formula on how to take the Laplace transform of the integral of any function. And that will be actually 1 over s, function of capital letter F as a function of s, plus small letter s, 1 over s, small f as at f sub 0 plus. Okay? That function now refers to I. So we replace the capital letter F by I now, because the variable we are considering for the meantime is current big letter I. Okay, I will erase this one. So what comes out? It will be A over S, R, I as a function of S, plus 1 over C, it comes from this. And the Laplace of the integral is actually 1 over S, capital letter F as a function of S, but for the meantime, that capital letter F is current capital letter I, so this should be capital letter I as a function of S, plus 1 over S, small letter I at f sub 0 plus. Okay? We must have to compute this value first before we can proceed. At time t equal to 0, assume the initial charge and the capacitor is 0. The initial charge is actually represented by the integral of I dt, and they should be equal to 0. At time t equal to 0, I sub 0 plus and the capacitor is 0. So actually, this becomes 0. Right? So if we try to bring out the simplification, it will be E over S equal to R, I as a function of S, plus 1 over CS. I bring out S over here. I multiply by C, so this is 1 over CS. I as a function of S, capital letter I, plus 0. 0 plus 0 or just simply nothing, right? And if we try to simplify this one, this now involves the so-called algebraic manipulation. I will factorial I as a function of S, so this should be I as a function of S, open bracket, R plus 1 over CS, R plus 1 over CS. The common factor is I as a function of S, and this should be equal to E over S. Solving for I as a function of S, that's actually our, what we call this, what we are looking for, I as a function of S. I as a function of S now will be equal to E over S. We will divide both sides by this quantity here, so it will become R plus 1 over CS. And by using, again, algebraic manipulation, it will just be simply E over S. Okay? I think I combine this one. It will be CS times R is actually RCS. So this is RCS plus 1 all over, this is all over CS. So again, algebraic manipulation, this should be E over S. Okay? We change the operation from division to multiplication. We take the reciprocal of the denominator, and the reciprocal will be, this will go up. So this will now be CS over RCS plus 1, close bracket. Okay? And luckily, this is here. Cancel with this. No more S. So what comes out? E times C will be easy. Okay? I will try to simplify this one. I will factor out RC. I will bring it out. So it will be RC. Okay? What remains inside will be S plus 1 over RC. Because RC times S is actually RCS. Right? And RC times 1 over RC is actually 1. So actually, we could factor out RC outside times the quantity S plus 1 over RC. And again, luckily, this C here cancel with this. Okay? So what remains? It will now be I as a function of S should be equal to what remains on the bottom portion is R and this quantity here. So I will just combine E over R, okay, times 1 over S plus 1 over RC. Okay, I think this will now the final formula before we will take the inverse Laplace transform. So I place it here, taking the inverse Laplace transform of both sides. Okay, I will check my camera. Taking the inverse Laplace transform of both the left and right. The inverse Laplace transform of capital letter I as a function of S is I, the one we are looking for. And the inverse Laplace transform of this quantity here, this portion, excluding E over R, because E over R is just constant. So this should be the inverse Laplace transform of 1 over S plus 1 over RC should be equal to, if this is plus, it will be E raised to the negative T over RC. It will be E raised to minus AT, where the value A is actually 1 over RC. So what comes out for the inverse Laplace transform of 1 over S plus 1 over RC is actually E raised to minus T over RC. So as a final solution now, the inverse Laplace transform of capital letter I as a function of S is small letter I, the one we are looking for, and they should be equal to, we will just take this value E over R, so it will be E over R times the inverse Laplace transform of this, which is E raised to minus T over RC. So this will be our final answer. Okay, I will erase this one so it looks good. This will be our final answer. As from the so-called classical solution, the current is actually E over R, E raised to minus T over RC. And the graph of this equation here will still be same as from the classical solution. The ordinate is actually the current, the abscissa is time. At time t equal to 0, the current is 0. Okay? So the graph is actually something like this. This is negative. So as time approaches infinity, the current is actually approaching 0. So it comes from this value here. Then as time passes by, the current will almost be approximately equal to 0. Okay, that's it, guys. That's the solution of the so-called series RC-DC using Laplace transform. Okay, so for those people who are taking up advanced mathematics, this is for you guys. If you want to subscribe to my channel is at youtube.com/@ProfDavidJ.Reyes, and if you want to share it, please click share. Good morning from Los Angeles.